Hi. Oop. Hi again without the echo. So today we are going to be doing a continuation of our last lesson. We are going to be comparing different substances. We're going to be comparing three to be exact. And I picked these three on purpose. So we are going to be comparing water, salt, and ethanol. Water, um, we're going to use twice. You're going to use in a mini lab and compare it directly to ethanol. And then salt, we're going to use later when I'm back, and we're going to compare water to salt. But for today, we're going to put all three in our same section of our notebook, and we're going to compare all three against each other. We're going to be comparing using the vocabulary terms from last lesson. So we're going to be identifying the different bond types that the substances have. We're going to be using the bond type to predict polarity level, high, medium, low, describe the regions, charged, fully charged, uncharged, partially charged, and describe electrons, shared, stolen, or equal versus unequally shared. So that's kind of our goal for today. And we're going to start with water because we all know it the best. So water, you see it everywhere on Earth. And we're actually going to start with the ball and stick structure for water. Red is going to represent oxygen. White is going to represent hydrogen. So this is our ball and stick model for water. And I'm going to keep the colors consistent today. So red is always going to be oxygen. Grab colored pencils if you want your notebook color coded. I would recommend it, especially since these notes are going to build your post-lab write-ups. Both the mini lab you're going to do soon and the bigger lab you're going to do with me when I get back. Okay, so I've got water. I've identified the elements. I've drawn the structure. In order to compare these substances, I need to identify their bond type. In order to identify their bond type, I need to figure out which electronegativity range they fall under. Now, electronegativities are set values. You look them up in tables. So you can look them up online. You can search these up on etable.com. However, for the sake of the video, I'm going to use a small copy of the periodic table that I have on my wall, and we can actually see the periodic table electronegativity values right on here. So if you look on the key at the bottom, now this does not look like the one on my wall, probably, because this is the back. The periodic table at the front of my classroom is not flipped over. It looks like this. So if you want to flip it over, and you can convince the sub to let you, that's just fine. Flip it over. This is what the back looks like. So the electronegativity value is the top number on the right hand side. So for oxygen, because that's my first element, the electronegativity value is 3.44. For hydrogen, the electronegativity value is 2.18. Now, I only need to look it up for each unique bond. So I only have one type of bond in water. I have an oxygen to hydrogen. The fact that that bond repeats, and I have two of them, is not significant when identifying the bond type. I only have one type of bond. It's between the element oxygen and the element hydrogen. So I only need to calculate one electronegativity difference. And calculating the difference is super easy. Big minus little 3.44 minus 2.18. I get a difference of 1.26. So from here, I can identify everything else. I can identify a bond type. And I can use that bond type to predict the polarity level, identify whether or not I have charged regions, and use that to describe the electron location along the bond. Okay, so bond type. Coming back to our notes from last class. Nonpolar covalent bonds were the first type of bond we had. They were a small or no electronegativity difference, less than 0.4. That is not what I have. Polar covalent bonds were a moderate electronegativity difference, which was any value between 0.4 and 1.7. What do I have? A number directly within this range. So I have a polar covalent bond, which means my level of polarity, I'm going to stick with my notes. I have a moderate level of polarity. Makes sense. This is kind of my middle level bond. My polarity level is moderate. So am I polar? Yes. Moderate strength. Do I have charged regions? Back to my sheet. I have partially charged regions on a polar covalent bond. And lastly, where are my electrons? Now, this I'm going to talk more in depth about today because I've got more models and I've got electronegativity values in front of me. Now, first thing we can identify using what we learned last class. In general, where are electrons in a polar covalent bond? So electrons are unequally shared. That much still true, but we can get more specific. We can actually figure out how they are shared. So remembering what electronegativity means. Electronegativity was the tendency to keep and steal electrons. Whoever has the higher value wants electrons more. Who here has the higher value? That would be oxygen. So where are the electrons going to be? Closer to oxygen. Because it has a higher electronegativity. So drawing those on the bonds, little bit of a skill. So each bond represents two electrons. The electrons are on the bond, but they're going to be closer to that red atom. Now, oxygen is going to have more than 4 total electrons, though. If you remember our Lewis dot diagrams, oxygen has 6 valence electrons. 4 of those were already paired. They are oxygens, and they are oxygens to keep. The other 2 are involved in the bonding with hydrogen. So those are the 2 that we're sharing here. So oxygen has 4 electrons it's keeping to itself, as well as 4 electrons that are shared on the bonds. Because oxygen has those electrons closer to it, This is going to be a negative region, while each hydrogen is going to represent a positive region. But because this is a polar covalent bond, we only have partially charged regions. So I'm using that open figure 8 symbol that we've learned about, not the fully charged ions that we would see if we had an ionic bond. Okay, so that's what we're doing today. Substance, using that substance, describing electrons, describing the regions, identifying a bond type. Water's done. Next substance, we're going to do salt. Salt is a general term in chemistry, but usually we refer to salt meaning table salt, which is going to be the substance sodium chloride, NaCl, which is the salt that you're going to be using in your lab. So sodium chloride, I'm going to pick some colors again. Sodium is going to be represented by the color yellow. Chlorine represented by the color green. Bond in the middle. Sodium yellow, chlorine green, bond in the middle. Okay, so same setup, same process. I'm going to look up electronegativity values on the table. Sodium is, lots of glare, 0.93. Because remember, electronegativity is going to be that top number on the right-hand side. Chlorine is 3.16. My electronegativity difference here, always big minus little. So 3.16 minus 0.93. And what is that going to get me? A fairly big value, 2.23. Now, if you remember our ranges, our largest range was, or our cutoff was 1.7. So the polar covalent bond that we just described above was anything between 0.4 and 1.7. If your electronegativity difference is bigger than that, you are no longer a covalent bond. You are a very polar ionic bond because you've got that large that word, difference. So bond type, and then I'll just list them all now because all going to be the same. We're going to look at bond type. We're going to look at polarity of that bond type. We're going to look at whether or not we're going to have charged regions. And then we're going to talk about and we're going to model what that means for the electrons. So bond type, already talked through and identified that. This is a very polar ionic bond. Polarity, yes, it's in the name. But the importance here is the strength level. This is going to have a high strength or a high level of polarity. Polarity is a scale or a spectrum. Every substance falls somewhere on it. What kind of regions am I going to have? All right, check my notes. Lots of checking notes when we're dealing with vocabulary. So what kind of regions am I going to have? Fully charged ions. What did my electrons do since I'm here? Well, they fully transferred. Okay, so how did they transfer? Well, using what we did above, electrons are going to be closer to the electronegative atom. So where are they going to go here? They're going to go to chlorine. They're just going to go all the way to chlorine. So now when I add my electrons onto my bond, I'm going to put them right next to the green atom as close as I can. And then chlorine is also going to have its 7 electrons that were already paired and uniquely it. What kind of charges is that going to get? Fully charged ones. One bond, which means this is going to be a full -1 charge because it fully took that extra electron. This is going to be a full +1 charge because it fully gave that electron that it did not want away. All right, so that's salt. Third and final substance, and it's third for a reason. It's a little bit trickier. Ethanol. Let's see. Try not to make it crooked for you. Ethanol is going to have a weird formula. CH3 CH2OH. And unfortunately, I mistyped this formula in your homework. So this is the correct formula. When you go to your homework today, which is going to be sheet 8, you're going to need to fix the typo. And it'll be clear, the typo. I'll have the word ethanol. I have parentheses. I have a formula listed after ethanol. It is not this formula. This is the correct formula for ethanol. This formula is written a little different than the formulas you're used to because ethanol is an organic substance, which means it's carbon containing, which means sometimes they have their own rules. This formula is written in a way that allows somebody with a little bit more chemistry than you guys have right now to predict the structure. But I can walk you through the structure. So the ball and stick structure for ethanol looks like this. Colors are intentional again. Gonna pick up my red. And switch to white. Okay, so this is ethanol. The white represents hydrogen, just as it did in water. Black represents carbon, and the red, just like it did in water, represents oxygen. So what this is a central carbon with 3 hydrogens bonded to it. That's the first part of the formula, CH3. The next part of the formula is CH2, which is what we see coming next. I have a carbon bonded to a carbon with 2 hydrogens. The last part of the formula is OH, which is oxygen, hydrogen, which is what we see. Carbon bonded to an oxygen bonded to a hydrogen. So this is written structurally. You can see the similarities. You are not expected to do that independently at this level, but that's where this is coming from. Now, when we are looking at ethanol, we have a few different types of bonds. First thing we need to identify is which bonds are we focusing on? So when we're dealing with polarity, we're mostly going to focus on the exterior bonds. So this carbon-carbon bond, there's only one of them and it's hidden inside the structure. So we're not going to focus on that. We're going to focus on the carbon-hydrogen bond and the oxygen-hydrogen bond, because those are the bonds that we see on the exterior of the structure. And just like the exterior of the atom, the valence shell, is the important shell. The exterior of the structure is going to determine a lot of the behavior of the structure. So I've identified my bond types on the outside. I also want to identify proportionally which bond type is going to be more significant. Carbon hydrogen, I have 1, 2, 3, 4, 5 of those bonds. Oxygen hydrogen, got 1. I also have a carbon oxygen bond in here that's also going to be predominantly internal because that carbon is tucked and hidden away. And this oxygen, we're already accounting for its behavior here. So I'm just going to focus on these two. Electronegativity values. Carbon is 2.55. And I've actually already looked up the rest. Because when we looked up water on example 1, we've already identified oxygen as 2.18. Hydrogen, sorry. And we identified oxygen as 3.44. So 2 different types of bonds. I'm going to need to calculate 2 differences. So big minus little, 2.55 minus 2.18. That's going to be small. That's 0.37. This is a little bigger. 3.44 minus 2.18, that's going to be 1.26. Now, these are different categories. 0.37 falls under our lowest threshold because our cutoff is 0.4. Our lowest threshold of 0.4, anything below that is a nonpolar covalent bond. However, above that, but below 1.7, which I am, we have a polar covalent bond. So this structure came last because it includes a few bonds, and those bonds fall into different categories. However, when we characterize the structure, we're still going to characterize the structure as a whole. And we're still going to use the same categories. We're going to talk about bond type, oopsie. We're going to talk about polarity, charged regions, and electrons. And then we're going to mark the structure up. So for bond type, well, we've got 2. We've got a nonpolar covalent and we've got a polar covalent. But when we're looking at the structure as a whole, most of the structure, 5 of the bonds, are going to fall in this category. So only a small portion of this structure is polar covalent, essentially only this little tail. So when I characterize the bond type, I'm going to say I'm mostly this. But I do have a small, with the letter S, polar covalent region. And I'm going to do the same thing for the other categories. I'm going to talk mostly for this nonpolar side. So my polarity is going to be mostly low to nonpolar with a small polar region. Which means my charged regions, again, mostly not charged, with a fairly small charged region. My electrons, what are they doing? Well, again, they're mostly uncharged. We're coming back to that nonpolar covalent bond type. That means we are mostly equally shared or fairly equally shared between the carbon and hydrogen portions. However, this polar tail is significant. So the electronegative oxygen, which is the largest value here, will pull the electrons toward it. So we are going to see this little tail have some charge trait. Because that oxygen is taking the electrons, it's going to have a negative trait. This hydrogen is going to have a positive trait. But most of the structure, no charged or non-charged. There's just one little part of the structure that has a charged component. So we've got three structures. We've identified different traits of each structure. Last thing we want to do, and you might be able to fit it on a page, but I'm going to need new paper. We want to rank them. And we are going to stack. We're going to rank them by polarity. Probably want the paper on the screen. So in my ranking, well, looking at what we have, my most polar, so I have a moderate strength, a high strength, and a mostly low strength. So my most polar is going to be salt with my ionic bond. My next is going to be water with my polar covalent bond. And then my least polar substance of the three that we looked at today is going to be ethanol with my mostly nonpolar covalent bond. Little bit of charged region on here, but for the most part, ethanol, nonpolar. So those are the three substances. These are the three substances we're going to be investigating throughout the end of the unit. Without me, you're going to compare water and ethanol. This is homework sheet 8. Don't forget to make that correction when you do it next class. With me, you're going to compare water and salt, and that'll be your major lab for this unit.